So, we've talked a lot about what chemical equations are, how they are used or why they are used, why we need to balance them, and we've looked briefly at a few different types of chemical reactions. Now, what we're going to do next is to actually take a look at some of the ramifications for when we balance our chemical equations. And the key thing that a balanced chemical equation is going to allow us to do is it will allow us to calculate how much of something we should be able to get if we know how much of a particular reactant we are actually using. So in essence, really, what you can think of, another way to think of your chemical equations, are they are sort of like recipes. They are similar recipes for making a particular product. Just like you need a certain amount of flour and all these other things um, to make bread, for example, you just need a certain amount of atoms to make up different compounds and different molecules. And we'll take a look at a simple example here, and we'll see how this really affects how we can use a balanced equation. So if I have the reaction between carbon monoxide, CO, and oxygen gas to make carbon dioxide. Okay. Again, now I would need to make sure that I balance my equation. And when I balance my equation, I need to insert my coefficients of 2 in front of CO. I have my 1 that's understood in front of the O2 to give me 2 CO2, 2 carbon dioxides, right? So the way that I would read this are a couple different ways. I can look at it from the perspective of individual molecules, okay, which is obviously a perfectly acceptable way to look at things, but realistically, that never happens, right? You don't deal with individual molecules and individual atoms. Instead, the way that your balanced chemical equations are going to be useful for us is those coefficients in the balanced equation. So the coefficients and the balanced equations actually give us a mole relationship, a mole to mole relationship between everything in that equation. And that's the key thing here now, everything in the equation. Okay, and there are two things I want to stress in this statement here in green. The first thing is that your equation needs to be balanced. Okay, that's really, really critical and why we spent a decent amount of time going through how we balance equation. The second thing here is it provides a mole to mole relationship between everything in that equation. So for example, the way that I would find this balanced equation useful for me, right, once it's balanced is as following. I can say, I'll try to keep this on here. I can say that 2 moles, and I can relate any two things in this equation as long as I have my balanced equation with the coefficients. I can say, for example, that 2 moles of CO react with 1 mole of O2. I can say that 2 moles of CO react to produce 2 moles of CO2. And I can also say that 1 mole of O2 produces 2 moles of CO2. Okay, all I'm doing, all of these numbers here, the 2s, the 1, the 2, those I get from the coefficients reading those coefficients. There's nothing really too complicated that I'm doing once I have my balanced equation. I can come up with these mole to mole ratios, which now you see here I express as equalities. Guess what I can do with an equality? Just like I can do with any other equality that I found anywhere else, starting in week 1 in our course. I can take that equality and I can make it into a conversion factor, right? So I can say 2 moles of CO over 1 mole of O2, or I can flip it. I can say 1 mole of O2 for every 2 moles of CO. So I'm relating now those two things to each other by whatever those coefficients are. Okay, and I can manipulate them like I can manipulate any equality. This is no different. This is absolutely the same type of manipulation we saw back within the metric system, for instance, where we converted centimeters to meters, right? There were equalities. 100 centimeter equals 1 meter. And you can put one over the other, or you can flip it. Same thing here. The only difference is where that relationship is coming from, and where it's coming from is from the balanced equation, just by looking at the coefficients. Okay, so when you take a step back and look at it, it is actually really, really straightforward to relate any two things. And that relationship, okay, again, is a mole to mole relationship in that chemical equation. When we use those mole to mole relationships in our chemical equation, we refer to that process, we give it a sort of a generic term, we call it stoichiometry. Okay, and you can add this to your list of big fancy words that mean really simple things. Stoichiometry simply means using the coefficients from the balance equation. And when we use them, we can solve all sorts of problems. We can calculate all sorts of things. Specifically, amounts is what we're looking at. Liters, they can be any other unit of amount that you can think of. Okay, that is what stoichiometry is. And it's a huge part of chemistry. Because guess what? In chemistry, we use and we perform chemical reactions, which we've just seen can be represented by these chemical equations. We balance chemical equations so we don't violate the law of conservation of matter. And as a result of balancing those equations, we indirectly come up with these mole to mole ratios, which is what stoichiometry is. Okay, and those mole to mole ratios are just the coefficients from the balanced equation. So let's take a look at an example that we have here. So it says, consider the complete reaction of 3.82 moles of carbon monoxide to form CO2. Calculate the number of moles of CO2 that could be produced. Okay, so first thing that you want to do is you want to make sure that you have a balanced equation. So we can say ensure that your equation is balanced first. And it is, because we're using the same equation that we used previously. Okay, and then relate, all we need to do is to relate or focus on, not relate, but focus on what you're given and what you need, right? Those are the things that we're trying to relate. Focus on what's given and what's needed. So here, we're given that we're starting off with 3.82 moles of CO. So that's this thing. And we need to figure out how many moles of CO2 is produced. That's this thing. Okay, these are the two things that I'm trying to relate to each other. I am not concerned about the oxygen now. That this is for what I'm trying to solve, this is irrelevant because my equation is balanced, right? And I'm just going to focus on the relationship between what I'm given, the CO, what I want, the CO2. The only relationship between them from this balanced equation are their coefficients, right? Which is a 2 to 2 ratio, and specifically that is a 2 to 2 mole ratio. Okay, so if I'm given 3.82 moles of CO, the carbon monoxide, from my equation, okay, I know that 2 moles of CO2 are produced for every 2 moles of CO that's used up. So I can set that up like a um, conversion factor because I know I've just listed over here in my list that 2 moles of CO equals 2 moles of CO2, right? So I took that and I made it into a conversion factor. I put the correct unit where I wanted it to be. If I want to end up with moles of CO2, I put the moles of CO2 on top and the moles of CO goes in the bottom. Moles of CO cancel. Obviously, 2 over 2 cancels into 1. So I get the same number of moles of CO2 at the end. And in a nutshell, that is what your stoichiometry is going to involve. Okay, that's the central part to every single stoichiometric problem is that mole to mole ratio. Okay, so let's write that because that's actually really, really important. The mole to mole ratio is the central part of every stoichiometry problem, which then suggests in order to do stoichiometry, again, should be your slogan or your what's the right word, your mantra as you go through stoichiometry. Okay, what you need to do is you need to get to moles, because only then, once you have the moles of something, only then can you use the mole to mole ratio from the equation to convert it to moles of something else. Okay, so in the same problem, if instead we're asked now, if we start with the same amount of CO, calculate the number of moles of oxygen needed. Okay, so now I'm given the CO. Now I want to relate it to the O2. Well, now I'm not concerned with the CO2 anymore because these are the two things, what I'm given, what I need, right? So again, I start off with what's given. My relationship now is the 2 moles of CO to 1 mole of O2. I want moles of O2, so that goes on top. Moles of CO on the bottom, they go away. I make sure I have the coefficient here, right? That's the 1, which is the moles, and then the 2 here for the CO that goes in the bottom. I take half of 3.82, which gives me the 1.91 moles of O2 left as the only unit in this problem. Okay, so every single stoichiometric problem will boil down to these mole to mole ratios that come from the balanced chemical equation. So what we can do is we can just summarize and we can say the coefficients from the balanced equation allows us to convert from moles of one thing to moles of any other thing in that specific equation. Okay, That's the key tenet of this here. And again, in order to use that, we need to get to moles.